Dear audience, greetings from Hungary. It is a great honor to be able to talk to you about the results of our previous researches. And Anil, thank you for the introduction. My first encounter with the Rocscience software family was in 2004. Since then, I have been solving a lot of tasks with these programs. And I am pleased to see that the programs have undergone many developments recently. One such key development is the creation of a dynamic engine in RS2 and RS3 codes. Now I want to focus on this topic, especially in the case of RS2. I have been working with a GeoSearch company in Romania on two important projects. Recently was carried out in 2019. An earthquake study had to be prepared for the entire road network of the Cluj-Napoca ring road, with particular detail on the area of the planned tunnels. Then in 2020, I conducted a study on the rock slopes of Csetățuia, where static and dynamic modeling had to be done. In my presentation, I will not go into all the theoretical and practical backgrounds describing the dynamic engine of Rocscience software, as these can be found in more details in the web help, and a longer webinar lecture on this was given by Dr. Qin Deng in 28 October 2020. What I would like to talk about the most is the conduct of a site-specific investigation, especially in the case of earthquakes. If we are already performing well-developed numerical modeling, we should also pay special attention to the production of adequate and accurate earthquake time histories. Don't be content with using unknown time series, perhaps just the envelope curve of the response spectrum defined by a few points offered by different standards, from which, to put it simply, we may produce synthetic time series for our work. Perform a complex and careful seismic hazard evaluation from which we can create much more reliable models by obtaining correct time series. This is important, so I will talk about this briefly. Here are just some points of our issues from the previous earthquake evaluation that I mentioned. Here we carried out a probabilistic seismic hazard analysis. And just some words let me say about this. So the term probabilistic seismic hazard analysis in a broader sense is used for all seismic hazard analysis methods which attempt to define either the frequency of events of earthquakes or the frequency of exceedance of secondary parameters. For example, specified ground motion levels. In general, any probabilistic hazard analysis method includes the following steps. You can see here a step. At the first step, it's important to make the source scenario, then magnitude recurrence relation calculations, then to choose a good and accurate attenuation relation. Then as a final processing procedure, we can get as final results the seismic hazard curves and of course the response spectra. One of the most important products of seismology is Earthquake Catalog, which provides a broad data set in earthquakes events. This can be used in various analyses associated with seismicity and seismotectonic hazard assessment and physics of earthquake. Earthquake catalogs are treated by two steps mainly. The clustering of earthquake catalog and determination of the minimum magnitude of completeness. The clustering seismicity is the method to sort out main shocks, foreshocks, and aftershocks in the catalog and removal of dependent events. Particularly, this technique is applied in earthquake prediction models and seismic hazard assessment. And maybe an important equation is here. This is the Gutenberg and Richter equation. Here you can see a worldwide earthquake hazard map. Here is Romania. Romania has one of the highest seismic hazard levels in Europe. A recent study by Pavel et al. 2016 shows that around 2/3 of the country has an expected peak ground acceleration in excess of 0.2 g. So this value is with 10% probability of exceedance in 50 years. Because the lack of time, we have no chance to explain the complex geotectonic and geological background. Just I would like to pay your attention that here is a important region. So mainly is the Vrancea region, which is very similar to the Hindu Kush region. Here is a profile, seismic tomography profile with the hypocenters. Here is also based on this information, it's visible, and there is a possibility to visualize how it's downing into the Earth's mantle, the continental slab at the Vrancea area. So that's why we have very deep hypocenters also, and middle depth, and of course shallow depth earthquakes in this region. Repeated large and intermediate depth earthquakes in Vrancea region shake several times Central and Eastern European cities, several hundred kilometers away from the hypocenter. So it's very important. Let's see some three-dimensional visualizations on this slab. Here is a 3D model based on 3D thermal investigation. Here you can see also a geological time scaling. So on the evolution of this enormous body. And here is another model based on seismic tomographic information. With the circles and asterisks are indicated the location of the magnitude of the seismic events. And just some information for our probabilistic seismic hazard evaluation. So we used mainly two important catalogs, the Big Cs and the ROM+, in our work until 2019, but I made also an update, so now we have until 2020. These are free catalogs. And during our work, we also made a checking by a special Hungarian catalog, and all are in the right place, and all parameters are correct in our models. Source models were used the Big Cs and the share model. So Big Cs is mainly used in Romania, and share is used all around Europe. And as background studies, Deák et al. And Pavel et al. Materials were used. Here you can see the used area sources during our modeling. This is the Big Cs and this is the share. So we have to mention that we didn't use faults as line sources or other point sources, so just area sources were used. And let's see, the declustering was carried out by using ZMap code. This code is using the Gartner and Knopf algorithm with the original window parameters. The declusterization was carried out by using this code. And of course, here at the right side, you can see a figure on the frequency magnitude distribution without declusterization. And here it's visible the results after the declusterization with the big C's source areas. The probabilistic seismic hazard calculations were solved by using the crisis free program. This program employs a probabilistic methodology to assess seismic hazard in regions. The required input data for crisis are the geometry of the seismogenetic sources, the seismicity parameters of the sources, and the ground motion prediction equations for seismic intensities. Each seismogenetic source can be represented by means of different geometrical models, such as areas, lines, or points. But as I mentioned, we use just areas. The seismicity of the sources can be considered either by Poissonian or non-Poissonian models. The seismic hazard assessment is performed for a grid, which characteristics in terms of spacing and shape are user-defined. And of course, the main equation used by crisis is the original Gutenberg and Richter equation, and a specific modified Gutenberg-Richter relationship, which calculates the annual rate of exceedance. Of course, to calculate the intensity exceedance rates in crisis, it is required the following. To define the zones where earthquakes are occur, seismogenetic sources, assign the magnitude recurrence relationships for each seismogenetic source, assign the ground motion prediction equation to each seismogenetic sources, and finally processing final results. The result is a hazard map, and by intersecting points, we can download the hazard response spectra and the intensity curves. Of course, during the processing, we have possibilities to use a more accurate and complex probabilistic evaluation. For this, during the probabilistic calculations, I used logic trees. In our case, I used a complex logic tree where the big C's model had 0.7 weight and share 0.3 weight. And of course, the big C's branch system is very similar to the Powell logic, to the logic tree used by Powell et al. But at the end, the branches are a bit changed, and of course, all ground motion prediction equations were changed to new and recent equations. In the case of shear branch, used a similar logic tree as we used in Hungary in a previous work. As I mentioned, we have at the final result a map, and anywhere if you make a click, we can export the hazard curve and the response spectra too. However, as a result of the study carried out in the framework of this project, the bedrock peak-ground acceleration and the response spectrum were calculated for entire Cluj-Napoca area, which were summarized in a map appendix, which maps were prepared by using QGIS. So we have selected the response time periods required for the construction of the design spectrum for future design work in accordance with the requirements of both Eurocode 8 and the Romanian regulations. These are the following response time periods: 0, 0.05, 0.07, 0.15, 0.4, 0.7, 2, and 3 seconds. For the following return periods were used: 95, 225, and 475 years. And another step is the site amplification. Seismic waves generally travel several kilometers in rock, but a few meters in soil. Yet the soil plays a very important role in determining the characteristics of ground motion and its analysis. The local soil conditions have a profound influence on the ground's response during the earthquake. Ground response effects are generally evaluated using one-dimensional models, which assumes the seismic waves are propagating in vertical direction through the horizontal layers of the soil. Theoretical modeling of one-dimensional site response can generally be accomplished using equivalent linear or nonlinear analysis. Equivalent linear ground response modeling is widely used in practice to simulate true nonlinear soil behavior. The advantages of equivalent linear modeling include small computational effort and few input parameters. The most commonly used equivalent linear computer codes are, for example, the shake, the deep soil, the proshakes, So we are using generally the deep soil. And of course, here you can see a figure on the concept of earthquake response spectra. So you can imagine if is coming an earthquake, you have several oscillators. You can imagine that these could be buildings with different resonant frequencies. And of course, it's visible. You have to imagine that, for example, the measuring tool, the seismometers are at the top of the buildings, and you will have different time series for different buildings, and of course with different frequencies. A kind of reverse work like the site amplification is deconvolution. In this case, you are going from the top to the deep parts of the model. So typically, we can get some measurements carried out from the Earth's surface, and if we have bedrock, we can assume that should be the same in the deep seismograms and the surface one. In this case, we have a possibility in RS2 and RS3 to use. Of course, user can input the seismic motion with using two options: a rigid base, where input motion, acceleration, velocity, or displacement is applied directly to the nodes, to the mesh. The base still reflects the downwards wave propagation back to the model. A compliant base where compliance will be activated when users select the compliance base option in the dynamic loading dialog. When compliance base option is selected, the applied motion will be transformed to applied force in this case. The choice of rigid or compliance base depends on whether the earthquake motion to be applied at the base of the model is outcrop motion or within motion. Outcrop motion are recorded on top of the rock layer, as I mentioned before, while within motion are either recorded at a specific depth from soil surface or computed by performing site response analysis. So in our case, if we have calculated bedrock information of bedrock response spectra, then we can get directly good time series. And let's see how it's working in the models. We have here an example, a project from Hungary. This is a slope, and generally we are using dynamic loads in XY direction too in the same time. But in this case, to check this opportunity, we use just the horizontal accelerations. And let's see the results. So we check this point here, and we check the X acceleration. And let's see, we have mainly around the maximum amplitude around 3.5 and 3.2 in this case. Of course, we had on this project also a deep soil, a calculation by using deep soil. Here you can see the profile used here with the layers. And of course, we can check that at the surface we have around 0.4 and 0.35 values. This is the response spectra summarization. So here is around 0.35. And let's see our deconvolution model. So at the beginning, at the first model, we introduced time history at the top here, but in this case we introduced acceleration, and in the results we exported data from this point, but the velocity data, and then we divide it with 2 because this option converts the then inputted velocity data to stress. So then at this model, in this model, we introduce the dynamic load here at the base. So this is the divided velocities. Here you can see, and we use compliant base with drift correction, of course. And let's see the results. Yes, here we used 100 sec for the time. And let's see now the acceleration again. And you can see that it's very similar, so around 0.3 G, 0.4, 0.35. Let's turn back to the presentation. And as a next step, we also used the calculated response spectra as target spectra for the next steps. In the next step, we downloaded some real measured time series from the online database from the Pacific Earthquake Engineering Research Center NGA West 2 database. And in this case, it makes a searching for the target spectrum, and typically we download 30 real accelerometers, and at the final detailed work we are using mainly just 5 time histories for this work. We are typically using the seismo match, so we have to make scaling work and then a matching work. And here is the final site amplification result on the tunnel areas. This is beside the Cluj city. At every site we had downhole measurements. Here you can see the threshold point. So here is the from this depth we have the bedrock around 30 meter in this case. So the bedrock is the threshold is at the 760 meter per sec velocity, shear wave velocity data based on the Euro code. And of course, after all evaluations, we have this surface response spectra for this area, for the tunnel area. But for the slope stability for the Csetățuia site, we calculated, of course, the bedrock response spectrum, and it was clear that also because we have rocks, we could use the calculated bedrock spectrums without site amplifications. In this case, so where we have scaled and matched time series, there we have chance to use also the downloaded vertical time series, matched time series, because always we have the measurements in XYZ directions. But in this case, where we don't use real measured time series, there is a possibility to calculate from the horizontal response spectra the vertical one with a empirical equation. Of course, from numerous exported crude compare modeling profiles was one chosen for the RS2 model. This profile is situated at the middle of the part of the this slope you can see here. And for the models, hybrid models, where we used also discontinuities, we also checked some typical discontinuity sets from the original engineering, geological, or geotechnical mappings. And during the numerical modeling, we use the main reason to operate with the factor of safety above 1.0. So another basic was the Eurocode 7 standard. Eurocode 7 represents a major change in design philosophy. With the Eurocode 7, partial factor of safety are applied to different components of the analysis. The partial factors are applied prior to the analysis of given design values. The final result is an over-design factor which must be greater than 1 to ensure the serviceability limit state requirement is satisfied in this case. During the modeling, we tried several model runs using homogeneous material model, and with several variations, we tried to introduce the documented discontinuity, as I mentioned earlier. Here you can see the models by using the discontinuity sets. Since that is not the focus of our presentation, I will not go into details, but once the model has been constructed, the shear strengths of all the component materials are iteratively increased or decreased by strength reduction factor until the slope fails. So we used the SRF solution, and we had stable slopes during the static work. For the dynamic investigations, we used the following time series. This is the horizontal, this is the vertical one. Also, in the past, we had to use several other specific softwares to make base corrections, to solve the filtering issues, but actually in the Rocscience now we have a developed engine which makes possible to solve these issues. You will see later on. So you can use the filter spectrum, baseline correction, filter data analysis, and to visualize amplitudes, also response spectra and areas intensity. During our modeling, we used 3 time queries, so 3 monitoring points, and during the continuum models, we had as final results accelerations and other seismograms without noises, and very similar to the original one, so to the input data. Then, in the case of hybrid models, where we introduced discontinuities, when the joint systems are used in the models, the behavior of the rock mass is different, as it happened at the previous case where we were using continuous material. In the case of the hybrid models, where are introduced the joint systems, the models not be discrete models, so the separated blocks have not independent degree of movement, but the discontinuities are behaving as boundaries between the separated continuous areas. The stress redistribution on the discontinuity boundaries is solved, and the physical conditions of the discontinuities are defined at a different solver than the continuous material. This behavior fact is also observable when it is used the dynamic examination. So the attenuation and amplification of the waves is blocked or staggered abruptly as the pass through the discontinuities, and this result is visible here exactly. And how looks like the models. So this is in the first case we just used the horizontal and then together with the vertical and horizontal, you can see here. And at the end, let me show just some calibration modeling work, because it was very important to us to check some results from our from other researches. And here is the first case when in the Batapati repository project we tried to use measured blasting acceleration time histories, and then together with earthquake we checked the extension of the excavation damage zone, so the change in the extension. And just some words about the models. So firstly, we had here the measurement point, and from here we made an amplification for the blasting time history, and then we loaded the tunnel wall, and then with using a Rayleigh damping of the previous amplified blasting time history, we rechecked the result, and you can see the final results how it looks like. You have to mention also that the damping of the soils and rocks is independent of the loading frequency. By contrast, Rayleigh damping formulation is frequency dependent and adequate to solve numerical damping. Use of Rayleigh damping in the numerical models allows the user to define the damping ratio for two thresholds frequency. Has a damping ratio lower than the specified damping ratios, and frequencies outside this range are damped more heavily. Numerous variation of the two frequencies and damping ratios were modeled, and the more appropriate result was set to the measured one in our case, of course. And what is important that, of course, during the measurement, the conventional work, tunnel work, was interrupted in both tunnels, and the ventilation system was turned off. So we could be considered seismically silent in the tunnels. So here is the 2 points, and let's see how looks like the model in reality. We can see that during the blasting we had very high frequencies. Here you can see on the spectrograms, and here you can see the final results. So on Excel it's more visible, so it's very similar. Just we had some noises in our results. Let's see another model. The amplitudes are very similar. And this is how looks like the model. It was an interesting situation because so for this kind of models we need to prepare a statically stable model, and then we start to input the dynamic loads. So here are the blasting loads, and then outside on the model we introduced the horizontal and vertical accelerations at the same time. And I would like to show you a final final calibration model. So this is from China. We we search for some special tunneling information regarding to the earthquake studies, and we have a article from 2016 about the Longxi Tunnel, and we were we were very appreciated to the Chinese specialists because they sent us the real measured time histories near to the tunnel. So it was a very good possibility to make a calibration on the earthquake issues. The Longxi Tunnel is located at a distance of 2 kilometers from the epicenter of Wenchuan earthquake. So here you can see the total length of the tunnel is around 3.6 kilometers, with a cross-section composed of 2 parallel twin tunnels, one for each direction, separated 30 meters between axes. And what is important that you can see here the used rock support system, mainly at this area near to the main fault. It was used shotcrete layers and also the pavement, a concrete layer with thickness 43 centimeters. The rock mass along the tunnel is organized into 3 classes based on the Chinese code, and also based on this information and based on the rock mechanical laboratory information, we made a parameterization of our model. The Longxi Tunnel, one of the most damaged tunnel is one of the most damaged tunnel during the Wenchuan earthquake. Suffered from small to heavy damage both at the portal and inside the tunnel, while sections close to the fault completely collapsed. This is important. The damage along the tunnel lining, according to the field investigation, is described in detail in the article, so I will not discuss on it more. We concentrate now on the fault area, where heavy damage occurred along the zone about 50 meters from the fault, where the rock mass class was 3. So here is. What is important that the authors used for the investigation the Abacus code, and in the Chinese investigation were considered 3 scenarios, one horizontal, so one horizontal motion only was used in the x direction. So in this case, x direction is here and z direction is here. And what is important that if we take into the consideration this fact, so at the Wolong Observatory we had a north-south direction and a east-west direction, and of course an up-down direction seismograms. So this is important if we put the whole system in space. Then they used another modeling, both horizontal x and z motions, transverse and longitudinal to the tunnel axis were considered without vertical accelerations, and all 3 motions at the third option. This is done to individually investigate the effects of the longitudinal and vertical accelerations on the response of the tunnel, since for the design those are often neglected in reality. So I also mentioned that it's very, very important to use not just horizontal, but also the vertical one too. And let's see how looks like our model. So this is an exported section from the Abacus software, and here is the photo on this region. So where is not collapsed the tunnel, there they observed at the uh, 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 tunnel also compression and tension areas. And in this model, you can see that here they in the reality and also in the modeling, they had a 2.9 centimeter uplift at the time of 13 seconds. And let's see our model. This is the model. So with the rock support, here are some time queries, some monitoring points. You can see also the horizontal and vertical information. Here I have to mention that we had a simplification mainly. We have to mention that because the tunnel axis is not aligned with the direction of motion recorded, as I mentioned earlier, at the Wolong station, it makes an angle of 33 degree with the horizontal east-west direction, and 57 degree with the north-south direction. So the horizontal X and the Z input motions are obtained by orthogonal decomposition of the recorded east-west and north-south accelerations. So our simplification is that we excluded this fact. So mainly we use our modeling the east-west direction and the up-down direction. And what final result we had, you can see here the maximum vertical displacements, and let's see the results. So the vertical displacement, let's see on the plot. So this is, and we can see here. So firstly, we used no drift correction, and then we had 2.85 centimeter between the minimum maximum displacement. So, but it's important that between 20 and 40 second. But at the second correct model, we use drift correction, and we have got 2.02 centimeter between minimum maximum displacements and between 7 and 12 secundum. So it's very similar result as came from China. And dear audience, thank you for your attention.